In this video, we are going to see how to obtain realistic images and animations of our projects created in Rhino using Rhino's Render. To start, we deactivate those layers that will not be relevant in this process, such as documentation or shading layers. And we visualize the model in 3D and in rendered mode. The first point to obtain photorealistic images is that each geometry or element has a material or texture assigned. We have already seen how to assign textures to Lang's elements during their creation. However, for Rhino's native geometry, we must apply a material to them. To assign a material to a geometry, we go to the Materials panel. The thumbnails at the top of the panel show each of the materials in the scene. The ones we already find created are those materials that have been automatically imported when inserting urban furniture blocks or people that we have incorporated into the drawing. To create a new material, we click on the Add Material icon. In this drop-down, we have several options. The first option we find is to import an existing material from the material library. With this option, the File Explorer opens so we can choose an already created material from the library materials. In this library, they are classified into different folders, according to type, and in each of them, we can view the thumbnails. I am going to look for a material with a grass-like appearance, and for that, I open the Organics folder. Once we select the material, we click on Open, and it is imported into the panel. To assign a material to a geometry, we can drag the material on the screen or first select those elements to which we want to give this appearance. And with the right button on the material's thumbnail, we select Assign Material. As you can see, we also have the option to assign materials to selected layers or to those layers where the selected geometries are placed. Each of these materials is defined by certain physical properties, such as roughness and opacity, and the base color, which can be provided by a color or by a texture image, and also an image for the bump. We commonly use a grayscale texture that simulates a relief on a surface without modifying its geometry. To create custom materials, we start with a custom material and edit its parameters and choice of maps or textures for it. For the creation of specific materials, such as metals, glass, or plastics, we start by choosing this type of material, for example, plastic material, and we limit ourselves to adjusting the properties provided so that it behaves realistically. In the scene, adjusting in this case the color, reflectivity, or desired transparency. Finally, we can also import these PBR materials, which are those based on physical properties, by using textures. Materials can use multiple textures to realistically simulate how light interacts with the surface, including details like glossiness, roughness, and relief. There are some platforms from which you can download free samples, such as the Ambient CG page, where we can find materials by type and download the necessary set of textures in a zip file. When we download these files, we return to the Properties panel, click on Import PBR material from Textures, and we can select the downloaded folder without needing to unzip it or unzip it and select the entire set of textures that this file contains. Each of the textures is automatically assigned to its corresponding property. And in this way, we already have the material ready to assign to the scene. After applying a textured material, we might need to adjust the scale or how the texture is projected onto the geometry. Although each texture can have its scale edited, the most convenient way is to assign a mapping to the object. We do this from the Properties panel, in the Texture Mapping tab, which appears when we have a geometry selected. If this message appears, we click on the blue button so that the object takes on the mapping we are going to configure. Depending on the shape of the element, we choose the mapping that will best fit. We have surface mapping, planar, box mapping, spherical, or cylindrical. For this wall, a box mapping fits us to be able to control the dimensions on all three axes, on the X, Y, and Z axes. We then click on the box mapping icon and now follow the instructions on the command bar. First, it asks us to select 3 points, just like when we model a box. The first 2 points define the vertices of the base rectangle, and the third will give it the height. This box that we are going to define is a reference for the dimensions. We can create it using the vertices of the geometry itself or in any space of the model. What we are generating is an invisible guide in the shape of a box, which will give dimension to the texture. Using the Show Mapping button, we can visualize this guide in order to edit, scale, or rotate it. A quick way to assign mappings would be by pressing the same mapping button. But instead of generating a box by entering points, select Bounding Box in the command bar, which will generate a box that encloses the selected object. We select which coordinates to use. I am going to use the universal coordinates. We indicate the option Yes when it asks about the capping, so that it applies the mapping on the top and bottom. And this mapping is automatically generated from a box of the necessary size to enclose the geometry we had selected. Now, to adjust the scale of the material or texture for this box, I hide the visibility of the mapping. And in size, using the lock, we lock the aspect ratio of the image so that when sliding the texture size on one axis, it scales proportionally on the other axis. When we have the scale set, if we want to adjust it on any of the axes, as is the case with the mapping in this direction, we unlock the aspect ratio using the same lock and adjust the scale on the corresponding axis independently. Once we have the scene ready with all the materials correctly assigned, it's time to define which view we want to render. To do this, we adjust the camera by moving it until we find the ideal framing, modifying the distance, direction, and perspective as needed. An additional parameter we can adjust in this process is the focal distance. This value is found in the Properties panel when no objects are selected and affects the scene's perspective. A lower value corresponds to a wide angle, which exaggerates depth and distorts the edges, while a higher value slightly flattens the image and reduces the sense of depth. When we have the desired view, we save it from the Saved Views panel. To do this, we click the camera icon with the plus symbol, assign a name to the view, and upon accepting, the view is saved along with a thumbnail in this panel. This is essential when we need to use the same viewing angle with different settings, whether for lighting or even to compare seasonal changes in vegetation. This way, whenever we move the view, we can return to the saved configuration by double-clicking on the corresponding thumbnail. We can save a multitude of views that we are going to render in this panel. If when changing views, we notice that it generates this animated transition from one to another, which slows down the process, we can disable it from the animation button by unchecking the box that indicates animating the restoration of the saved view. This way, the change between views will be immediate. Alright, now we open the rendering panel where we configure the parameters for the final render. In the top drop-down, we select the render engine we are going to use. If we have other engines installed that integrate with Rhino, like V-Ray, they will also appear in this list. In this case, we will use Rhino Render. In the View section, we choose from which perspective we want to obtain the rendered image. We can select the current view, meaning the view that is currently active on the screen, or directly select one of the saved views. To define the quality of the final image, we adjust the resolution in pixels. The first field corresponds to the width and the second to the height of the image. We can enter custom values or choose from the suggested options in the drop-down. Besides the size, we also define the render quality, which is measured in the number of samples. The higher the number of samples, the greater the accuracy in light calculation and, therefore, the longer it will take to process. For test renders, therefore, we use a low quality, which allows for quicker adjustments, and for the final image, we will increase this quality to achieve a more precise result. In the background section, we define what will be seen in the areas where there are no objects in the scene. We can assign a solid color. By default, this is shown in white, and by clicking, we can apply a different color. We can also select the use of a gradient, which creates a transition between two different color samples. Lighting is key to obtaining a good render result. We can configure two types of light. Skylight, which adds a diffuse global light, providing uniform illumination to the scene. And sunlight, which works like a real sun, generating more defined and contrasted shadows. Let's see the difference. If we render with only skylight, the lighting appears flatter and softer. However, if we activate the sunlight and perform the same render, here, we observe more pronounced shadows with greater contrast in the scene. To the right of the sun, we find a button that opens the sun panel and a floating window. From this panel, we adjust the parameters to achieve a realistic simulation of sunlight on the project. In the Options section, we can define the orientation of the north either by interacting with the circle or by entering an angle manually. We also have a slider to regulate the intensity of the sunlight. We can control the position of this sun in two ways. The first is automatically. In this mode, the sun will adopt a position and height based on the date and time, simulating the real lighting for this time of day and season of the year. The first slider adjusts the month of the year and the second defines the time of day. As we approach dusk, the lighting takes on a warmer and darker tone. At the bottom, we can specify the geographical location and time zone of the project. To do this, we select a point on the map or choose a country from the list. This mode is ideal for shadow studies and realistic simulations in the project. On the other hand, if we check this box, we gain manual control of the sun. If we activate this option, we lose the date and time-based configuration and can freely adjust the position of the sun by modifying the altitude and azimuth angles. Since this mode does not depend on a specific location, it is useful for quick and customized lighting adjustments. Another option for the background is to apply a 360-degree environment using an HDRI image. The peculiarity of HDRIs is that, in addition to serving as a background appearance, this environment will affect the scene's lighting, acting as a light source for the skylight. If we click on Import from the library, we have several options to choose from depending on the type of theme. We find studio environments or outdoor environments. We can also create or edit an environment with a downloaded HDRI image. In this case, I will select an HDRI of an outdoor landscape as the background image. These images include a light point that corresponds to the sun's illumination. Therefore, if we are using the skylight in the scene, the position of the sun in this image will also determine the direction of the shadows. We must understand that this image is applied by wrapping the scene as if it were a dome. We can adjust its rotation to modify the position of the light source and the background. Using the altitude value, we control the height of the horizon. And the intensity value is the same as that of the skylight. In this case, I will not use the skylight in the scene or the environment for reflections. As we can see, the environments are not visible in the view, but they do appear in the render. These backgrounds can have difficult scalability, and the size of the image may appear large in proportion to the scene. To solve this, I will try repeating the image vertically so that the scene captures only the lower half. This result fits somewhat better in scale, although I am going to reduce the sun's intensity to 0.8. If we can't fit an environment into the scene, we can render with a transparent background and apply the context in post-production, since when rendering, we will also obtain the alpha channel. Another resource sometimes used is to place an image directly in the model. We draw a vertical surface where we want the background texture. I will move it back so that the wall's shadows are not projected onto the image plane. I return to the view of our render. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . We create a material from an image by loading a representative image of the environment and assign this material to the created surface. We adjust the position or give it a texture mapping if necessary to control its scale and position, and then render it. When rendering, we have this image added as part of the environment. As I mentioned, if we activate the transparent background when rendering, we can also save the alpha channel to make post-production and editing of this background easier in an image editor. When we want to obtain the final render, we make sure to have selected the appropriate view and adjusted the quality before starting the process, and once configured, we press the render button at the bottom to generate the image. Remember that in the vegetation tutorial, we saw how the slider in the Document tab, within the Edit panel, allows us to define the seasonal appearance of the plants. Unless we have manually overridden the season by species, the vegetation will automatically adapt to the selected seasonality. This means that, depending on the configured season, the render will show variations in the appearance of the plants, reflecting the seasonal changes. Now, we click on the Render button and the process starts directly in a separate viewing window. The render is progressive. This means that the image is generated in several passes, refining the quality as the number of samples increases. At the bottom of this dialog, we can see the sample counter, which indicates the level of detail reached at each moment and the elapsed time. When the render is finished, the message "Render Ready" will appear, indicating that the image has reached its final quality and is ready to be saved. If at any point we consider that the quality is already sufficient and we don't want to wait any longer, or if we need to cancel the process, we can manually stop the render with that Stop Render button. To save the image, we click on Save Render, choose its location, and assign a name. If we look at the tools in the Visualization tab, in addition to finding the commands to control the layout of views, the model view, and the display modes, we find the access to start the render with the quality set in the properties. Additionally, we also have the option to preview render, which performs a low-quality render that, as you can see, reaches a total of 10 samples, allowing us to evaluate the lighting and composition before launching the final render. If we have closed the render window, we can quickly access the last completed render using the button Open Last Render. To edit a saved image, we have the Image Filters tool, which allows us to load an image and apply visual adjustments like sharpness, brightness, or a portrait effect to this image. By selecting a filter, we can adjust its intensity and parameters, and if we want to apply it, we click on Add. We can also combine several filters or remove them with the Remove button. Among the available artistic filters, we find pencil, ink, or oil effects. To compare the changes applied with the original image, we can keep the original button activated, which shows us the render just as we loaded it. If we are satisfied with the editing, we save the new image with the Save button. Other useful visualization tools to get a realistic idea of the impact and scale of our design are setting the viewpoint and walk mode. By setting the viewpoint, we define a first point that positions the observer, represented by a human silhouette. If we use the eye level option, suggested by the command bar, we can enter a value to adjust the camera height, which also scales the silhouette proportionally. Then we indicate a second point that defines the direction in which the observer is looking. This is an alternative way to set the camera's viewpoint, obtaining a perspective similar to what a person would have within the design space. The walkthrough mode introduces us to the project from a human perspective, but also allows us to navigate and move through the space. With the cursor, we control the direction we are looking, and using the keyboard arrows, we can move through the model, whether forward, backward, or sideways. In walkthrough mode, as we move through the space, the elevation of the terrain and elements like ramps or stairs are automatically detected. This tool is very useful for obtaining a realistic spatial impression, controlling visibility from various points of the project, and evaluating distances, passage spaces, or the height and thickness of incorporated elements. One of the interesting features of RhinoLands is the ability to create small animations from the animation panel. From this panel, we can animate both the movement of the camera and the seasonality of the plants. To animate the camera, we first define its path. We can leave it at a fixed point by clicking on the button, choosing a path, and defining a point in the drawing. In this way, the camera will remain in one position without moving. Or choose the curve option to create a path using a previously drawn curve. For example, let's draw a curved line that starts from the bottom of the stairs, goes up, and turns to the left. I modify the elevation at each of its control points. And now, with the Choose Path button, I select this curve as the camera's path. At the top of the panel, we have this player that allows us to preview the animation in the view. By pressing play, we see how the camera moves along the defined path. Below the player, we find several options. First, we have a box where we can assign a name to this animation. Let's call it Walkthrough. And we also see the frames per second. These define how many images are rendered per second of animation. The total duration of the animation is shown under the parameters according to the current settings. The duration depends on the speed of the camera, which we control using its slider. The faster it moves in kilometers per hour, the shorter the duration of the animation will be. If we want to input a specific duration, we activate the duration box and enter the time in seconds. This deactivates the speed control, as it will adjust automatically. If we activate the Look Forward box, the camera will always look forward along the defined path. And within this path, we can adjust its angle on the X and Z axis to modify the orientation during the journey. If we deactivate the Look Forward option, we can select the point of view using a fixed point or define a view curve that indicates the visual path. For example, as a fixed point, we can keep the view fixed on this tree here. Or select a curve that defines a path. I will copy the camera's path curve and move the endpoint. With this, we make the camera start by looking forward and then continue its path focusing on the second curve. As I mentioned, we can also animate the seasonality of the plants so that there is a variation in seasonality throughout the animation. We need to select the season at the start of the animation and which season we want it to have reached by the end. The animation settings can be saved in the Rhino file, allowing you to store several different animations. To do this, we must name them and click on the Save button. The saved animations will appear in the drop-down menu. To export the animation in video format, at the bottom of the panel, we define whether we want to render the animation as it is shown in the view, or with Rhino Render to obtain a more realistic render in each of the frames. We choose the destination folder and define whether we want to render the entire animation or just a specific range of frames. Finally, we click on Render to start the export. The process will sequentially generate the renders for each of the frames, which will be combined into a final video file in MP4 format.